Welcome back to today's video. In today's video, we're going to discuss experimenting with attribute combinations in our data. In particular, we're going to take a look at attributes in our data that may not be very useful to our machine learning model and experiment with that data in order to make it data that may be useful to our machine learning model. Before we get into today's video, make sure you hit the subscribe button down below and like the video for more content just like this. And so let's go ahead and start off by taking a look at what we discussed in the previous lecture. And so in the previous tutorial, we discussed how exactly we could determine the correlation between each of our data. In particular, we're taking a look at the standard correlation coefficient, the Pearson R correlation coefficient. And we took a look at what data had to be removed from that data. In particular, we had to drop the ocean proximity. And the reason for that was because that was non-numerical data. From there, we then took a look at what the correlation between each of the data was to all the other data. And so we took a look at longitude, for instance, and we compared it to all the other data, including itself. We took a look at latitude, and we compared it to all the other sets of data. And so what we were able to do was we were able to see how, when one data value goes up, how the other value goes either down or up, and how exactly that's correlated. And we took a look at each of those data sets. And then from there, what we were able to do was we were able to take a look at particular attributes that we were concerned with, and then we were able to observe how they were correlated using graphs. And we were able to particularly zero in on this particular graph right over here, which compared the median house value to the median income. Taking a look at that graph right over here, we notice that this graph had a correlation coefficient of 0.68 roughly. And what that demonstrated was the fact that as the median income values went up, the median house values also went up as well. Now, in today's video, we're going to take a look at some of the data attributes that were not very useful to us, but we're going to take a look at how exactly those data attributes can be made useful for us. Going back to our data set, let's take a look at some of the attributes. In particular, let's start with the total rooms. The total rooms is not very useful to us. The total rooms, remember, represents the total number of rooms for an entire district. Each row in this data set represents a particular district, and the total number of rooms refers to the total number of rooms in an entire district. The same thing with total number of bedrooms, and the same thing with population. Notice that we also have a household attribute in our data. The household attribute indicates the total number of households in a particular district. How can we make the data more useful? Well, when it comes to total rooms, why don't we take a look at the total rooms per household in order to know what the average number of rooms are, the average number of rooms per household in a particular district. That will give us a better representation. And for the total number of bedrooms, why don't we divide that by the total number of rooms in order to know what the bedroom to room ratio is for each of the homes on average in each of the districts. And so in this case, the total number of bedrooms would refer to the number of sleeping rooms that have a bed in them, and the total number of rooms would refer to living rooms plus washrooms plus all the different rooms that you could have. By gauging that data, we'd be able to see how exactly house prices go up or go down based on what the bedroom ratio is to the number of rooms. Then we can also look at population, and we can compare population to the number of households in order to gauge what the average population is for a particular household in a particular district. All right, so let's take a look at that data and how exactly we can do that. To begin with, let's start with dividing the data out. So we have your rooms per household equals housing total rooms divided by housing households. Now, what we're going to go ahead and do now is print that data out, and let's take a look at what those data sets are, what the data values are rather. And so we see here for rooms per household, remember, each row represents a particular district. And so in this case, we got that the average number of rooms per household in district 0, I'll call it district 0, I'll refer to it by an index value, is 7, basically 7. So that's the total number of rooms in that particular household, in that particular district, on average for each particular household. And so on average, it ranges roughly from 5 all the way up to 8 on average, it looks like, just taking a look at it. Obviously, we can determine the average as well by just adding up, just taking the length of this, dividing it by the length, and we'd be able to get an average, right? And so, yeah, you could just add them up, add up each of the values, and then just divided by that. All right, and let's take a look now at the bedrooms per room. Bedrooms per room compares the total number of bedrooms to the total number of rooms. So just basically gives that ratio. So for example, if you had 5 bedrooms in a particular household, or let's say 2 bedrooms in a particular household, and you had 10 total rooms, that ratio would be 0.2. And so we would expect for this one we would expect decimal numbers, because the total number of bedrooms is always going to be less than the total number of rooms. And so in this case, we got decimal numbers like 0.2, 0.15, 0.2. We're seeing on average it's roughly around 0.2. So what that demonstrates is that on average, in each household, in all of the districts, on average, of the total number of bedrooms, we have 20% of the bedrooms in each total number of 20% of the rooms in each household will be bedrooms on average in each particular district, in each particular household. 20% of the rooms will be bedrooms. So that means if we had 5 rooms in total, one of the rooms will be a bedroom, and then 4 of the rooms, which is the complement of that, will not be bedrooms. And so we see that there. Then we have total population divided by total number of households. And what we get there is 2.5, 2.1, all those different data sets. And so that what that simply represents is that we have roughly around 2 to 3 people per house, basically, in each particular district, in each of those districts. All right, and so that data obviously will be much more beneficial to us. Now that we have these individual data values, let's take a look at how exactly we can push them into our housing data frame. And so we see here that we have our housing data frame object, and we're pushing each of these data values into that. So we have the column attribute, and then we're assigning a value to it. A column attribute name, and then we're assigning a value to it. With that being said, now let's go ahead and print this out in order to see how the housing data frame object will look like. All right, so now we printed that out, and we were able to get these values here. We notice here that we have the values that we had before: longitude, latitude, housing median age, total rooms, total bedrooms, population, household median income, median house value, ocean proximity. Let's take a look at the values right over here. Rooms per household, bedrooms per room, population per household. So we're able to add those values to our housing data frame object. Now remember, a housing data frame object is not the entire data set that we have in our housing.csv file. Rather, it is a stratified training sample that we were able to get. So going back to the lesson in which we did that, I believe 2 or 3 lessons ago, or I think 3 lessons ago rather. Remember what we did here was we said that the housing data frame is now equal to a stratified training set, and we were able to copy that over. So remember that the housing data frame object is not necessarily the housing CSV file object data set. Rather, it is a stratified sampling of 80% of the housing.csv file. And remember, the housing.csv file is roughly 20,000 rows, and so if it's 80% of the housing.csv file, that would mean that it would have roughly 16,000 rows in that particular training set. Now that we've added it to our housing stratified training set, let's go ahead and take a look at how exactly we can observe the correlation. First of all, what we did here is we had the housing data frame, and we removed the ocean proximity column. And the reason why we removed that was, remember, the ocean proximity column was non-numerical data. And obviously, in order to calculate the standard correlation coefficient, or the Pearson-R correlation coefficient, we must engage in numerical attributes. And so because of that, we removed any alphabetical letters, any columns that contain alphabetical letters. And so we removed the ocean proximity column. Now, ocean proximity, if you could potentially represent that by numbers. And so if you take a look at the ocean proximity, we have here near bay, we have inland, we have basically about less than 1 hour away from the ocean. We have basically 3 values for our ocean proximity, 3 values. What we could do is if we wanted to assign this in a numerical way, maybe we could say near the bay, we can assign it to a value of 1. Or something like inland could be a value of 0. Less than 1 hour away from the ocean could be a value of -1. We could assign numerical attributes potentially and determine the correlation coefficient from there. All right, but for now, we just have it in alphabetical letters, and so we're going to remove that. The reason why we're going to say axis equals 1 is because of the fact that axis equals 1 says that we're removing a column attribute. If we say axis equals 0, that means we're removing a row. All right, so axis equals 1 just means we're removing a column. And then we're calling the correlation function on that. And then from there, we're able to calculate what the correlation is for every single column. And remember, we're comparing every single column to all the other columns. Okay, so if that were to be the case, you would get roughly around you would get in this case, how many columns do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, I think 10, right? 10. And then we also added in our 3 here. We added in these 3, so it'd be 13, right? We'd get 13 different columns there in that case. But we're focused particularly on the median house value. And so we said sort values ascending equals false. It's going to be in descending order from highest to lowest. Okay, let's take a look at this here. We're able to get these values. Now, taking a look at this, we have median house values equal to 1. What are we comparing each of these values to? Well, we're comparing it to the median house value. And an easy way to get that, if you're just taking a look at this, is number 1, we have median house value over here. But also, if it has a correlation of 1, which remember that's a linear correlation similar to this, which is it's a y equals mx plus b line, considering that every value overlaps with the same value. Even if we have like an opacity of 0.1, it would still overlap, which would be that for an alpha value. And let's take a look though at how this is related. So let's take a look at number 1, median house value would be the same. Median income, we already covered that. But let's take a look now at the data values that we're concerned with. Total rooms, and comparing that to the rooms per household. We can see that the data really isn't that different. Rooms per household, remember what the 0.15 indicates. It indicates that as the median house value goes up, the rooms per household will also go up, but not by as much, right? So it's going to be a weak linear relationship, essentially, if you wanted to phrase it that way. Total number of rooms, as the total number of rooms per district goes up, as the median house value goes up, the total number of rooms is also going up, but it's going up by a very, very weak number, right? So if, for example, if the house value, for example, were to go up by a value of, but were to 10x, then the total number of rooms would also increase. It wouldn't decrease, but it would go up by, let's say, 1x or something. It would just increase by just a tenth of that factor, essentially. All right, and so we have their total rooms per household as well. And so you're not really seeing a difference among that data. But let's take a look here now at total bedrooms, and then we'll compare that to the bedrooms per room. We're seeing that as the household value goes up, the total bedrooms does go up, but it's going up by a very small percentage. If you want to calculate the percentage from a decimal, you just multiply it by 100. And so in this case, it's going up by roughly 5%. Okay, so not a very weak correlation there. But let's take a look now at the bedrooms per room. That's going to be negative 25%. So as you can see there, that as the house value goes up, the total number of bedrooms per room goes down by not necessarily a strong factor, but it is 0.25 is not as low as something like positive 5%. All right, and so you're seeing that there. So that's interesting there. Bedrooms per room. Now remember, bedrooms per room simply represents the ratio between the number of bedrooms relative to the total number of rooms. And so in this case, what that means is that as the house value goes up, the number of bedrooms relative to the number of rooms in each household on average in each particular district goes down. And so what might that mean? Well, that might mean that as the house value goes up, you may see more normal rooms compared to the number of bedrooms. And so it's easy kind of just to print this data out, but you need to be really able to interpret the data. And so you see here total bedrooms per room, that as the number of rooms increases, as that denominator increases, and as the bedroom number either decreases or stays the same or doesn't increase by the same ratio, that's going to result in a higher housing price on average. Okay, and so that might mean because it's more spacious, right? Typically speaking, residential homes have a smaller or a little bit of a less ratio, or not a less ratio, but a higher ratio when it comes to bedrooms per room. So it'll be something like 0.6 or something like that, maybe potentially. I'm going to go and look at the data again. But on average, what you're seeing there is that as the median house value goes up, the bedrooms per room goes down. And I think it was way less than 0.6, by the way, as well. But let's take a look at now as population. You're seeing that as population goes up by roughly 3%, it goes down as house value goes up. Population per household, it's a very similar number as well, roughly 3% going down as well as house value goes up. And so that's what our data was. And remember, by the way, we're saying this all in reference to this value right over here, 1. So keep that in mind as well. All right, so that was our lesson for today. It was a very shorter lesson compared to previous lessons. In the next lesson, we're going to get into data cleaning as well and taking a look at how we can clean our data